we're devoting this entire section to talking about the normal distribution because it's such an important distribution for modeling real-world phenomena. And because it's so important, because it comes up so often, we're going to break it down into several pieces. Here, we just want to talk about the mean, variance, and standard deviation that are associated with a normal distribution. So as a reminder, a normal distribution is a distribution whose probability density function looks like this. So if the probability density function is f of x, then this curve here is modeled by this function f of x. Because of the shape of the normal distribution, we often call it a bell curve as well, although there are other distributions that have bell shapes. So this particular kind of bell shape is not exclusive to a normal distribution, but all normal distributions do have this kind of symmetrical bell-shaped curve or bell-shaped probability density function, which is centered at the mean of the data, which if we're talking about a population, we indicate with mu. If we're talking about a sample, we indicate with x bar. And that's right at this point right here, the center of the normal distribution. Now, when we're talking about a normal distribution, we have to keep in mind that we could still be referring to either a population or a sample. Remember that a population is the entire group or set that we're studying, whereas a sample is a small subsection of that population. And we distinguish between these two things because, let's say, for instance, we're interested in surveying the entire population of the state of California. We know right away it's going to be very difficult, if not impossible, to collect survey responses from every single person, every single citizen of the state. And so instead of attempting to ask every person in the state the same survey question or to gather data from every person in the state, the entire population, instead we'll take a small sample. The goal, of course, is to make sure that our sample is representative of the population. But that's an entirely different topic, figuring out how to take a sample that isn't biased, but instead is representative of the population. Now, for a normal distribution, our formulas for mean, variance, and standard deviation will be different depending on whether we have data from the entire population or just from the sample. Of course, keep in mind that normally we'll have sample data because, practically speaking, for real-world problems, it is usually difficult or impossible to collect data for the entire population. But to distinguish between these two groups, we want to indicate the size of the population with capital N and the size of the sample with lowercase n. So if you see capital N, that means we're talking about the number of subjects in the entire population. So if we're talking about the state of California, this capital N would represent the number of people in the entire state. If we see lowercase n, it means that we've taken a smaller sample of the population, and the number of people in our sample is given by lowercase n. So let's say based on what we're studying, not related to the California example, our population is 10,000. Well, capital N would equal 10,000. We might take a sample of, let's say, 1,200 people, and then lowercase n would be equal to 1,200. So these are the sizes of the population in the sample, capital N and lowercase n. And then the mean of the population is given by this formula here, whereas the sample is given by this formula. Notice that they are identical, except for two things. First, in the population mean formula, we're dividing by capital N, whereas in the sample mean formula, we're dividing by lowercase n. And of course, that makes sense based on the fact that we're using capital N and lowercase n to represent the size of our population and sample, respectively. And then the only other difference is the notation that we use to indicate the mean, which we talked about earlier up here as the center of the normal distribution. The population mean we indicate with this Greek letter mu, and the sample mean we indicate with x bar, this x with a bar over it. But other than that, the formulas are identical. So all these formulas are telling us is that to find the mean, we are summing up all of the possible x sub I values, all of the values that our variable takes on. And after we sum them all up, then we divide by either the number in our population, if we're finding population mean, or the number in our sample, if we're finding sample mean. So add up all the data points, divide by the number of data points we have. That's all we're doing to calculate the mean of the normal distribution. Now, for the variance, this should look familiar because we've already looked at mean, variance, and standard deviation formulas. But for the normal distribution, just to confirm here, all we're doing with the variance is taking all of the data points that we have, all of the x sub I values that we have in our data set, and for each one, we subtract the mean here. So notice that the formulas for population and sample are again almost identical. All we're doing is taking the individual x sub I values in our data set, and that goes for population and sample, and then we subtract the mean. And of course, if that's the population, we're subtracting mu. If it's the sample, we're subtracting x bar. But in either case, we're just subtracting the mean. And that gives us the deviation for each data point. So this is the deviation of the individual data point x sub I. When we square that value, we now have a squared deviation or a squared difference. And then this summation notation just tells us to sum up all the squared deviations. So once we expand out to this part of the formula here, this is just the sum of all the squared deviations. And again, notice that up to that point, our formulas are identical except for the mean being represented by mu or x bar. And then in the summation notation for population, we're summing up to capital N. For the sample, we're summing up to lowercase n. So really, no difference at all, practically speaking, between the two formulas up to this point. We're just taking the sum of all of the squared deviations. But then for population, we divide by the number in our population, capital N. But for the sample, you might think that we would divide by lowercase n the number of subjects in the sample. But in fact, and this is the most interesting part of all of our formulas for mean, variance, and standard deviation for a population and a sample, this particular piece right here is the most interesting part of our formulas. And the reason is because we would think it's n, but it's actually n minus 1. And that's because when we take a sample from a population, we inherently introduce some bias. It's virtually impossible for our sample to perfectly represent our population, for us to be able to scale up our sample data to perfectly match our population. For example, maybe we're working with a population of people, and let's say the population is 1,000 people, and we'll even say that exactly 500 of them are women and 500 of them are men. We might take a sample of 100 people, and even though we randomly sample from the population, meaning that we are randomly, blindly choosing one person at a time from the population, putting them back in the population, and then pulling out another person, and we're collecting a sample of 100 people from that population of 500 women and 500 men. When we sample that way, and we collect 100 people, we might get a sample that's, let's say, 52 women and 48 men. That's not going to scale up perfectly to 500 women and 500 men. Our sample is going to be a little bit different in terms of its representation of the population. We are just hoping and implementing some good sampling techniques to try to make sure that the sample is as representative of the population as we can possibly make it. But no matter what we do, we're likely going to introduce bias. And so because we introduce some bias when we sample from the population, it turns out that because of that bias, using this n-1 figure to calculate variance actually helps us undo a little bit of that bias, as opposed to just using lowercase n, the number of subjects in our sample. So we use this n-1 value to get a better approximation to get rid of some of the bias we introduced by sampling instead of using the full population. So when we calculate variance for a sample, we have to remember to divide by n-1 instead of just lowercase n, the number of subjects in our sample. So if we take a sample of 100 people, we would be dividing here by 99 instead of dividing by 100. So those are our population and sample variance formulas. And then, as you already know, standard deviation will always just be the square root of variance. Now, if we want to see these formulas in action, of course, the easiest way to do this is going to be to use a calculator or a computer to help us make these calculations, especially as our data set gets larger. Because you can see here, let's work with a data set that I've already created. This data set only has 10 data points in it, and already look at all of the calculations we're doing, much less if we have a data set of 1,000 subjects or even more. These calculations quickly become impossible to do by hand. But here's what we've done here to calculate mean, variance, and standard deviation for this particular data set. Let's walk through this step by step. So what we're going to say is that maybe we're a distribution company we're running a warehouse and we want to get information about the age of the employees that work in the warehouse. So what we're going to do is we're going to take a sample of 10 employees. So we're going to say lowercase n is equal to 10. We're going to be using a sample instead of surveying the entire population. Maybe we actually have 200,000 warehouse workers and we're not going to be able to ask every one of them for their age. So instead, we're going to take a sample of 10 employees. And all we're doing here, we're not talking about at this point whether this is a good sample. We'll talk about sampling techniques and representative samples later. All we're talking about now is how to calculate mean, variance, and standard deviation for this sample. We're using age in this example only because age, as long as our population is large enough, is going to be normally distributed around some mean. So we're going to say here that our sample size is lowercase n equal to 10. We surveyed 10 employees. And this second column here of our table are all of the responses we got. So we asked 10 warehouse employees their age, and we got all 10 ages here. And then to calculate sample mean, so we're calculating here x bar, we found that x bar, the sample mean, was equal to 43.2. And we find that by taking the sum of all of these ages and then dividing by n equals 10. So we would take here to get x bar, the sample mean, this is how we calculated 43.2. We would take 43 plus 35 plus 38, so 43 plus 35 plus 38, and we would continue adding until we got to the very last age here, 40. And then we divide that entire sum by the sample size, n equals 10. And we see that here in our sample mean formula. We sum up all of our data points, all of our x sub I data points, and then we divide by the sample size, n equals 10. And the result there is a mean of 43.2 for the age of those 10 employees. Now to find variance for our sample, we take each one of our x sub I values and we subtract the mean x bar. So that's what we're doing here in this column. We're finding all of the deviations. So we're taking 43 and subtracting 43.2 to get negative 0.2. We're taking 35 and subtracting 43.2 to get negative 8.2, all the way down until the last data point. And so this second column here is giving us this x sub I minus x bar value for each data point. Then in this last column here, we're squaring each of those deviations. So negative 0.2 squared is a positive 0.04. Negative 8.2, when we square it, is a positive 67.24. So we square all those values. Now we have all of our individual squared deviations, this part of the formula. Then our summation notation here tells us add up all of those squared deviations. So we have all of our squared deviations, and then we add them all together to find this sum. Now we have the sum of all of our squared deviations, and then all we have to do to find variance is divide this sum of all the squared deviations by, and remember, n minus 1, because we have a sample, not a population, and when we find sample variance, we have to divide by n minus 1 to undo some of that bias. So here, this value for variance is not 1007.6 divided by n equals 10. It's 1007.6 divided by 10 minus 1 or divided by 9. So when we divide the sum of our squared deviations by n minus 1 equals 9, instead of n equals 10, the result we get is 111.96. And so this is our variance, 111.96. And that's an approximate value because we're rounding there to the nearest 2 decimal places. So that's our approximate variance. And then, of course, to find standard deviation, we just take the square root of variance. So standard deviation will be equal to the square root of variance, which in our case is approximately the square root of 111.96, which is approximately 10.58. And so our standard deviation for the sample is approximately 10.58, just over 10.5. Remember, and we talked about this before, that the mean is this center of the data. The standard deviation is the figure that we'll use as a measure of spread. Mean is a measure of central tendency. Standard deviation is a measure of spread. So this figure tells us how much this data is spread out around the mean. Remember that if our standard deviation is smaller, it tells us that our data is more tightly clustered around the mean, which means all the data gets sucked in closer to the mean, and our normal distribution might look something more like this, with a taller peak and smaller tails, where all this data is pushed in closer to this center, the mean. Whereas if our standard deviation is larger, it tells us that our data is pushed further away from the mean. It's more spread out. This measure of spread is larger. And so our normal distribution might look something a little bit more like this, where we have fatter tails and the distribution is shorter. The data is pushed out further away from the mean because of that larger standard deviation. And we'll talk more later about how we use and interpret mean, variance, and standard deviation. The primary goal here is just to understand how to calculate these three values for a normal distribution for both a population and a sample.